Human error causes over 90% of auto accidents every year, resulting in the deaths of 30,000 people. This error can be eliminated through the use of autonomous vehicles. That's why tech giants like Google, Tesla, and Uber are pouring resources into the development of autonomous vehicles. If you live in San Francisco, you're likely to see these driving around the streets. If you go to MIT, you're likely to see these driving through the tunnels. At MIT, we have the opportunity to make our very own self-driving car in the course 6141, Robotics, Science, and Systems.
The robot we've been using, which our team calls the Green Machine, is a Traxxas rally car at a 1 to 10 scale, equipped with an NVIDIA Jetson Tegra X1, a LiDAR unit, a stereo Z camera, and a wheel odometer. Over the course of the semester, we've used these instruments to allow our robot to autonomously follow a path, localize itself, and detect objects. For the final challenge, we have developed our robot system to drive autonomously through the Stata basement while navigating around orange and green cones, passing them on the right or left according to the color. This challenge is made up of two parts. Part 1 is following a path around the basement, and Part 2 is avoiding the cones. For path planning, we decided to use a manually entered path, rather than a path that is dynamically updated as the robot drives through the basement. We made this decision because path planning algorithms have a long runtime, and for this challenge, they were unnecessary. We created the path in the visualization tool RViz by manually selecting points and connecting them to form a trajectory. Our robot uses a pure pursuit controller to follow this path at a constant speed of 0.5 meters per second. In a pure pursuit controller, errors in the trajectory are determined geometrically. The controller guides the robot in a stable arc-like path to reach the specified reference point.
While driving along the path, the robot's LiDAR is continually scanning, looking for cones. If the robot detects an object that is less than 2 meters away, our image processing algorithm analyzes the object using the Z camera input. The algorithm checks if the color of the object is within the HSV range corresponding to the green or orange color of the cones, using a technique we had learned in a lab earlier in the semester. If a cone is identified, a marker is added to the map, and the trajectory is updated so that the robot will swerve left around orange cones and right around green cones. Given the proper hardware, sensors, and preliminary guidance, our team of 6 undergraduates was able to work over the course of a semester to deliver an autonomous vehicle capable of navigating around objects and completing loops around Stata basement. Larger teams of engineers use the very same fundamental principles we learned about in 6141 to deliver vehicles to the public that are safer and more efficient because of their autonomy software. For us, learning these skills and being able to contribute to the field is an important step in being involved in the evolution of transportation in this era. Some people claim that fully autonomous vehicles will only become a part of everyday life in the far future. However, now that we understand the fundamentals of how self-driving technology works, we are confident that the days when we no longer need driver's licenses are coming very soon.